Okay, as in with the previous problems, to get the best results out of these examples, if you will stop the video or pause it after I've asked a question or asked you to do a calculation and do the question or the calculation on your own, and then compare it to the answer I give and find out if and where you went wrong. This time we're going to be looking at external work and change in gravitational potential energy, usually denoted as U sub G. Potential energy requires two objects interacting via a force. Why? If there is no interaction, there is no potential energy. So we start off with an object positioned at the initial height yi, and we're going to move it up with an applied force to final position yf. That's your force applied. Of course, if we're moving it at constant velocity, which we'll be doing, then your applied force will be equal and oppositely directed to the force of gravity, F sub g equal mg. What is the work done on the system, object plus Earth, by an external force raising the object from yi to yf? No acceleration. What is the definition of work? Of course, the definition of work is that work external will be equal to the applied force and the scalar product of the differential, dr. What is the force in terms of unit vectors? Well, we usually assign the positive j unit vector for moving vertically up. So the force applied would be the magnitude of the force applied. And the magnitude, of course, is nothing more than just this quantity right here and j hat, the unit vector denoting the y direction. What is the differential displacement in terms of unit vectors? Well, if you recall, we're dealing here with this dr. And so what is dr? What is the differential movement? It's in the dy direction. So that will be dy j hat. And once again, the unit vector j hat denoting the y direction. Calculate the work done. Well, go ahead and evaluate that integral. You know what the applied force is. It's just a constant. And you know what dy is and you know what your limits are. Okay, and it's simply going to be the integral from y to yf, f applied, j hat, scalar product dy j hat equal to, we can pull the f sub g out because it's constant and we're just integrating over dy. And now what is this term here? Okay, you should know that. That's simply 1, and the integral comes out to be mg yf minus yi. And we denote that as mgh. So the work done is just simply mg, the force from gravity, times the height through which that force was displaced. If I release the object at height h, does it have the potential to do work? Is energy stored in the system? Yes, it can both do work and energy is stored in the system. We now define gravitational potential energy as mgy, and the advantage of this function is that the change in gravitational potential energy only depends on the initial and final height. It does not matter how you got there. We call such a force a conservative force, and we'll talk more about that. Need only evaluate the function UG, the potential energy function, at the endpoints YI and YF. End of discussion.